Welcome to this lecture series in real analysis. We will continue our discussion with continuity, and in this lecture we look at the Epsilon-Delta Criterion for continuity. So let us recall the relevant things. In the previous lecture we defined the notion of an epsilon band. So if we have a point on the plane, call it a comma b, and epsilon is a positive real, then the epsilon band about this point, or I don't know, however you want to express it, the epsilon band about this point is the following region. You draw a horizontal line epsilon distance above b and draw a horizontal line epsilon distance below b. So this line is y equals b plus epsilon, and this is y equals b minus epsilon. And everything that is sandwiched strictly between them is the epsilon band about a comma b. This is not a standard terminology, I just invented it for my purpose. Okay, and we defined the meaning of continuity, which I named as the geometric definition of continuity. This is not how textbooks express the definition of continuity, but there is a reason why I did it that way, and that will become more apparent as we go further in this lecture series, especially when we discuss derivatives. So fix a function from a set S to R. The set S can be arbitrary. There is no assumption on the set S. And of course, we need it to be non-empty. And fix any point in S. Then we defined the function f to be continuous at the point x0 if the following happens. If for all epsilon greater than 0, there exists delta greater than 0 such that the graph of the restriction of f to this delta neighborhood is contained in the epsilon band about the point x0, fx0. So a complicated looking definition, but if you decode it, what it is saying is we have some point x0. Let me edit this figure. So suppose I have this point x0 and a function has been given to me, something. For the sake of understanding, it is better to think of S as the entire set of real numbers. So some function is given, and let's say the point x0, fx0 is here. And then we choose an epsilon, fix an epsilon and draw the epsilon band. Okay, and what is it saying? It is saying that we call f to be continuous at x0 if no matter what epsilon has been chosen. So we have chosen some epsilon. We should be able to find a delta such that the graph of the restriction of f to this delta neighborhood, since S, we are thinking of S as all real numbers, this intersection is just this much. So the graph of f above this or restricted to this region is contained in this epsilon band. So if you choose a delta is small enough, then all the points in this region, their graph under the function f will be contained in the epsilon band. So this should feel like a correct definition. We discussed it for a sufficient amount of time in the previous lecture, and today it will be more or less a reformulation of the same thing. Okay. Here is one problem for practice. And now let us get started. So this is called the Epsilon-Delta Criterion for continuity. Textbooks define continuity usually this way, but I first defined it in a different way, and then this is now a theorem. Some definition was given, which I called the geometric definition. This becomes now a theorem. So what is the theorem or lemma? Fix a function from a set S to the real numbers, where S is a subset of R, obviously, and a non-empty one, and fix a point x0 in S. Then the following are equivalent. First statement is that f is continuous at x0, so all that grisly geometric definition. And the second statement is this, which is, it looks quite similar. For all epsilon greater than 0, there exists delta greater than 0 such that whenever we pick a point which is delta close to x naught, which is same as saying whenever you pick a point x in the delta neighborhood of x naught and simultaneously choose it in the domain of f, the distance of the image of x under f from fx naught is at most epsilon, is less than epsilon. So it already looks quite similar to the geometric definition, and that is not an accident. Actually, this is very, there's nothing there. This calling it a lemma is an exaggeration. It's immediate from the definition, and you may question why didn't I just define it this way? There is a good reason. When we discuss derivatives, the way I defined this will be more apparent as to why I did that. Okay, so let's at least write something. It's so similar, these two statements, that it's difficult to write much. But let me at least try to prove 2 from 1 and leave the other direction as an exercise. So what is the proof? So assume 1, want to show 2. Okay, so to show 2, fix an epsilon. Fix a positive epsilon. And we want to show that there is some delta with this condition satisfied. Okay, so by the geometric definition of continuity, we know there exists a delta greater than 0 such that the graph of the function restricted to this region is contained in the epsilon band about this point, which means what? If you decode the definition of graph and epsilon band, it just means that whenever you choose a point in this region, whenever you choose here, we get that this point is in the epsilon band about the point x naught comma fx naught. Okay, so this definition is exactly saying that. But what does this mean? This means the same as, or an alternate way of writing it is this. Implies, and what does this say? What does this guy say? We have x comma fx lying in epsilon band about this point. That is same as saying the distance of fx from fx naught is at most epsilon, strictly less than epsilon. So that's just saying that this happens. So a very straightforward massaging of or decoding of the definitions leads to our conclusion. And if you reverse the steps, you will be able to prove 1 from 2. So that's it. Very silly proof, if you want to call it that. Okay. So let's end this lecture by working out an example. We understand a definition once we use it, we understand it when we think about it, but also especially when we use it. So let's look at an example. Keep this criterion in mind. This is called the Epsilon-Delta Criterion of continuity. Okay, so we want to show the following. We have this function f which takes x to the square of x for all x, and we want to show that f is continuous. So let's just show that f is continuous at 1, and the similar proof will go for other points. So we have this point 1 whose image is also 1 because the square of 1 is 1. And we want to show that f is continuous here. So to do that, we will choose some epsilon, and we want to produce a delta which satisfies the Epsilon-Delta Criterion. And before we do that, we may assume that epsilon is less than 1. If we can produce a delta which responds to a smaller epsilon, we can produce a delta which responds to a bigger epsilon. So this is not losing anything. So for this kind of epsilon, we will produce a delta. And let me just produce a delta. So choose delta as epsilon by 4. You will see where this comes from. This is not some just some rabbit out of a hat. If you work it out, this is a result of a back calculation. If you try to work the proof out, this is one value which works. Infinitely many other values work, but this is one convenient choice. Okay, so what do we need to prove to establish the Epsilon-Delta criterion? We need to prove the following, is that if, or we claim that if x is in this region, 1 minus delta, 1 plus delta, then this is the case. If you call this point as x0, then the left side is x and x0 minus delta, x0 plus delta, the delta neighborhood of x0, and the right side says that fx and fx0 are at a distance less than epsilon. So this will establish the Epsilon-Delta criterion and hence prove continuity of the function at 1. So why is this? Very simple. Fix some x, and we want to show this holds. So write x as 1 plus y. So if we have a point x in this region, we can write it as 1 plus y for some y within that. So that's very clear. And now, what is fx? By definition, it is x square, which is 1 plus y square, which is that much. And that gives us okay. But by this constraint, we have the following inequality. But now by the choice of delta, what is delta? It is epsilon by 4. Okay. And unfortunately, I've run out of space. So let me try to make some. All right. So what is this thing? This is equal to, right? But since epsilon is less than 1, epsilon square is less than epsilon. So this whole thing is less than epsilon by 16 plus epsilon by 2, which is less than epsilon. So basically, this whole thing is less than epsilon. So what have we done? We have shown, all this reasoning shows, this shows that fx minus 1 is less than epsilon, and similarly one can show this is greater than minus epsilon. Okay, by a similar argument you can show this, and if you combine this with that, you get that. Because what is it saying? It is saying precisely that this is the case. Okay, so that proves continuity at 1, and I hope it has given you some insight as to what is going on when we say f is continuous at a certain point. Alright, so with that I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.